Good day everyone, my name is James Brian Manatad from grade 12 Mendel. Our topic for today is sound waves. Objective. First, describe qualitatively and quantitatively the superposition of waves. Second, apply the conditions for standing waves in string and relate the frequency, source dependent, and wavelength of the sound with the motion of the source and the listener. Sound waves. Sound waves are longitudinal mechanical waves that travel through gases, liquids, and solids, causing variation in pressure and density. The simplest form is sinusoidal, characterized by frequency, amplitude, and wavelength. Sound typically spreads outward from the source, with amplitude decreasing with distance and direction. Sound waves are a type of wave that moves through air, water, or solid materials, causing changes in pressure as they go. They're like vibrations that move back and forth in the same direction the wave is traveling. The simplest type of sound wave looks like a smooth wave sinusoidal and has three main features. The first one is frequency, how fast the wave vibrates. Next, amplitude, how strong or loud the wave is. And the last one is wavelength, the distance between two peaks in the wave. When sound moves away from where it started, it spreads out, and its strength or loudness decreases as it travels. Superposition of waves. Superposition is a fundamental principle in wave mechanics, where two or more waves overlap, combining to form a new wave pattern. The resulting wave depends on the amplitude, frequency, phase, and direction of the individual waves involved. Superposition can be described both qualitatively in terms of behavior and quantitatively using mathematical formulas. When two or more waves meet, they combine and make a new wave pattern. This is called superposition. The new wave depends on the loudness and frequency of each original wave, how the waves match up in timing, the direction they are traveling. Superposition is like overlapping sounds. For example, if you hear two people talking at once, the combined sound you hear depends on each voice pitch, volume, and timing. Characteristics of waves. The general motion of elements of air near a vibrating object is back and forth between region of compression and rarefaction. This back and forth motion of elements of the medium in the direction of the disturbance is characteristics of longitudinal wave. The motion of the elements of the medium is a longitudinal sound wave, is back and forth along the direction in which the wave travels. By contrast, in a transverse wave, the vibration of the elements of the medium are at right angles to the direction of travel of the wave. When a sound is created like when an object vibrates, it pushes particles in the air back and forth. This makes areas of higher pressure and lower pressure that travel through the air. This back and forth movement along the same path as the wave is what we call a longitudinal wave. In contrast, transverse wave, like waves on a string, move particles sideways relative to the direction of the wave. Interference. Interference is a phenomenon in which two coherent waves are combined by adding their intensities or displacements with due consideration for their phase difference. This can create a wave with high intensity known as contractive intensity interference if the waves are in phase. A wave with lower intensity called destructive intensity if they are out of phase. Interference occurs when all types of waves, such as light, radio, surface, water waves, gravity waves, and it can also be seen in electrical waves from loudspeakers. Interference happens when two waves meet and combine, depending on how their high and low points match up. They can either add together to make a stronger wave or cancel each other out, making a weaker or even zero wave. Here are the types of interference. First, constructive interference. is when two waves traveling in the same direction overlap and their crests combine to produce a larger waves. This occurs when two waves line up so that their high points and low points match perfectly. The waves add up to create a bigger wave, making the effect stronger. Example: imagine two speakers playing the same sound at the same time. If you stand in a spot where the sound waves from both speakers meet up in the right way, where the loud parts line up, the sound will be louder. This is because the waves add up, making the sound stronger. Second type of interference. Destructive interference is when two waves traveling in the same directions are aligned at the crest of the one wave and the trough of the other. The waves cancel out. This occurs when two waves line up so that the crest of the one wave meets the trough of the other. When this happens, the waves cancel each other out, making the effect weaker or even silent. Example is when two sound waves with different frequencies overlap and the noise level or volume decreases. Bits. For sound waves, interference of nearly equal frequencies produce intensity variations called bits. The closer the two frequencies, the longer the period between bits. Bits occur when two sounds with close but not identical frequencies play together, creating a pattern of rising and falling loudness. As frequencies get closer, the beats slow down. Pilots use this effect to match airplane engine sounds by making the beats disappear, and musicians do the same to tune instruments. Pilots and musicians use beats to match sounds accurately by adjusting until the beats disappear. Beat frequency. Beat are the periodic variation in the loudness of two sounds played together. Beat frequency equals F2 minus F1. Example: what is the best frequency at 256 Hz and at 260 Hz tuning? The fork are sounded together. Beat frequency equals 260 Hz minus 256 Hz equals 4 Hz. Standing waves. Standing waves are actually the result of the superposition of two traveling waves with the same wavelength and frequency moving through each other. As their amplitudes add together, they produce standing waves. These waves are formed by the superposition of two or more moving waves. The waves move through each other with their disturbances adding as they go by. If the two waves have the same amplitude and wavelength, then they alternate between constructive and destructive interference. The resultant looks like a wave standing in a place and thus is called a standing wave. Standing waves form when two waves with the same frequency and wavelength move through each other in opposite directions. As they overlap, their amplitudes add up, creating points that appear to stand still. Properties of standing waves on a string. Nodes are points of the standing wave that do not move at all. This is where destructive interference is always occurring between the two traveling waves, making the standing wave. Nodes are points that don't move because of constant destructive interference. Antinodes are points of the wave that move the most. Antinodes are points that move the most, where the wave's amplitudes add up fully. These waves look as if they're standing in place, even though they are created by moving waves. Relating frequency and wavelength sound. Frequency. This is how fast the sound waves are produced. If the source vibrates faster, it creates a higher frequency, which means more waves in a given time. This makes the sound higher in pitch. Frequency is how quickly sound waves are produced. A higher frequency means more waves in a short time, creating a higher pitch sound. Wavelength. This is distance between one wave peak and the next. If the frequency is higher, the wavelength gets shorter, and if the frequency is lower, the wavelength gets longer. Motion of source and listener. If the source moves towards the listener, the sound waves get squished together, increasing the frequency. This is called the Doppler effect. If the source moves away, the waves stretch out, lowering the frequency. When a sound source moves toward you, the waves are compressed, making the sound pitch higher. This is the Doppler effect. If the source moves away from you, the waves spread out, lowering the pitch of the sound. In summary, standing waves on a string need fixed ends and a specific length that matches whole wavelengths. For sound, the frequency and wavelength are related to how fast the source vibrates, whether it's moving toward or away from the listener. That's all. Thank you.